We will back to the class. Now, in the last class, we have done this Apriori algorithm, and we have showed you that using this particular example, that how from a database you can generate the item sets. Now, here, as I told you earlier, you start from the list of L1, then from L1 we generate C2, from C2 we generate L2, then C3, then L3, and so on. And at the end, when there is nothing to be left, that is the set of items which are having the minimum support. Now, based on this example, I already gave you that how you are going to generate the candidates key. And you know that when I am generating the candidates key, you are trying to self-join LK with LK. And therefore, when you are going to do a self-join, you will get the candidates keys, and from those candidates keys, you have to select those candidate keys which are having the minimum support. Therefore, what we are going to do is that if the support is less than the minimum support, we are going to do the pruning step. That means those candidate keys has to be removed and they are not put into L of k. Okay. Now, this is the explanation that, for example, I start with say L3 over here, and I start with say some L3, and based on this L3, suppose I have ABC, ABD, ACD, AC, and BCD. If I am going to join say L3 with L3, what I get? I get ABCD from ABC and ABD. Okay. Similarly, I get ACD from ACD and ACE. And therefore, if I get these two candidate keys, what I have to do is that I have to check whether it survives the pruning step. If it is not survive, it has to be pruned. And therefore, ACD is removed because AD is not in L3. Now you know that any particular subset, if it is not frequent, the superset will never be frequent. This property, what we told in the last class, is called the anti-monotone property. Okay, and therefore we are ending up with only ABCD, which is a frequent item. Now, based on this, let us try to understand this one. Now, here this is just an example I am going to do. If I get this ACD, I have all the subset of ACD, which could be ACB, ACE, AD, and CD, because we want subsets of size 3, and because I want to put it into L3. Now, when I am going to put it into L3, it has to be size 3. Therefore, I have the size of item sets as of 3: ACD, AC, AD, and CD, and therefore I have to keep only those ones which are frequent over here. Okay, and these two survives, whereas AD doesn't survive because ACD is not frequent. Now, the question comes: how to count the support of candidates? Now, why this is an important problem? Because the total number of candidates which is there will be very large, and therefore you cannot directly use a simple scan method to scan the database from 1 to n, because that one transaction may contain many candidate keys. Why? Because the transaction may be very long. It can contain say 50 items, and from those 50 items there could be many candidates which will be frequent, and from those frequent items we have to try to find all those frequent items which are there in one transaction. Therefore, if you just simply use a normal scan method, that means you are just going to do a lookup, this will not solve the problem. Now, what should we do? Therefore, in that case, what should be done is that we have to maintain the candidate keys in the hash tree. And when we are going to when we are going to maintain a hash tree, what happens? The leaf node of the hash tree contains the list of item sets in the count. Now, when I maintain a hash tree, the leaf nodes of the hash tree will contain the item sets as well as the count of those item sets. Whereas the interior nodes, the nodes which are not leaf, that contain the hash tables. Okay, and the subset function will find all the candidates contained in the transactions. Now let us try to understand how to maintain a hash tree. Okay, then what we are going to do is that when we are going to count the support of the candidates, we have to maintain a hash tree. Now let us try to see how the hash tree will be maintained. Now let us take an example. Here, suppose with some transaction, I end up in getting these 15 candidate keys, which are having a length of equal to 3. Okay, and these 15 candidate keys are to maintain in some hash tree. Okay, try to understand it very well because this is the basis of improving the Apriori algorithm. Now, as you already know, that when we are going to take a hash function, we have to first of all pick one hash function. Now, for the convenience, I use a simple hash function as mod 3. Mod 3 means when you divide a number by 3, the remainder what is given will be the number which will be used in the hash tree. Now, what I do is that at the first level, now suppose this is the hash function which I have designed. Now, I have a number from 1 to 9, and therefore 1, 4, 7 will come this side, 2, 5, 8 will come this side, and 3, 6, 9 will come this side. Why? Because 1, 4, and 7, when divided by 3, will give a remainder equal to 1. Therefore, what happens? This will be having a remainder of 1, this will be having a remainder of 2, and this will be having a remainder of 0. That means the left hand side will contain all items. When applied, the hash function mod 3 will generate a remainder 1. Whereas the middle one will generate a remainder through 2. And the right hand side will generate a remainder 0. Because when we apply a mod 3, there could be only 3 cases. Either there will be no remainder, or there will be remainder 1, or there will be remainder 2. Okay. Now when I apply this function, suppose I am going to do the hashing on the first item. Now I take the first item, this one, 1, 4, 5. Now when I divide the first item 1 with mod 3, I get remainder 1. Therefore, this will come on the left hand side. This will come on the left hand side. Okay. Now I take another item 1 to 4. Again, when I divide 1 with mod 3, again I get remainder as 1. Therefore, this will also come in here only. Now we do it 4. Again I divide 4 with 1. Sorry, 4 with 3. It gives a remainder 1. Therefore, this will also come here only. And therefore, these 3 which I am going to use right now, these 3 are all matching to this side. Will all match to here. Will all match to here. Now I take the second one. I am going to take the second one. And the second one which I take is 1 to 5. Now 1 to 5 also matches to this one only. Therefore, in that case also, this will going to match to here only. Then 4, 5, 8. Again, this will match to here only. 1, 5, 9. This will also match to here only. 1, 3, 6 will also match to here only. Why? Because you check, I just mapping with the first one. This one. Okay. Because I am going to match on the first item, and the first item is 1. Okay. Therefore, it is 1, 1. Now here the first item is 4. Here the first item is 4. And now let us try to come to the other one. Now here, now I start with this 2, 3, 4, and I apply 2, 3, 4. I divide 2 with 3. I get a mod 2 divide mod 3 will give you 2. Therefore, this will map to here. 5 will also map to here only. Then again 3. 3 is having 3 mod 3 will give you 0. Therefore, this will map to the third one. And all this having 3, 3, 3, 6, 3 and 3 will all map to the right side. Because you are mapping them based on the hash function mod 3. Correct? That means all these items are mapped to the either the left or the middle or the right. But once I am maintaining a hash, I will have a maximum length of the hash table, and therefore I cannot accommodate all those numbers in one hash table. Therefore, what I have to do is that I have to do on the second item. Therefore, now what I am going to do is that I am going to do on the second item, and therefore what I am going to do, I am going to map with this one, these items. Now you remember that all 1, 4, 5, 1, 2, 4, 4, 5, 7, 1, 2, 5, 4, 5, 8, 1, 5, 9, 2, 1, 3, 6 were all mapped to the left hand side. Therefore, I start mapping with this 4. 4 mod 3 will give you 1. 4 mod 3 will give you 1. Therefore, here this will map to the left hand side. Then 2 mod 3 will give you 2. Therefore, this will come on this side, the middle one. Then 4, 5, 7 will also give you 5 mod 3 will give you 2. Therefore, this will also come in the middle one only. Then 1, 2, 5 will again give you remainder 2. Therefore, this will also again come in the middle. 4, 5, 8. This will give you remainder 2. Therefore, again this will map to the middle only. 1, 5, 9 will give you remainder 2. Because 5 mod 3 will give you remainder 2. This will also come in the middle only. 1, 3, 6 will give you remainder 0. Therefore, this will map to the right hand side. And therefore, what I am going to do, I am trying to find all those items which are being mapped over there. Similarly, I will do it for the middle one, and therefore you find that I am having this 3 and this having 6. This is the hashing on second item, and 3 mod 3 will give you 0, 6 mod 3 will give you 0. Therefore, this will only be the same leaf. Similarly, I bring it for the third one, and I will be able to find that those items will come in either the left or the right or the middle. Then I do on the third item, and third item in this case will be 5, 4, 7 and so on. And then I am going to use the mod 3 with them, and I will be able to find all those items will be mapped to the leaf over the leaf. Now when I am going to do this, what happens is that you are going to map them into one of the particular leaves. Now when I am going to do all this, what happens that you are left with this items and the leaves. Now just a moment. Okay, just I will use this again. Now based on this, I will be getting these items at the leaf, and therefore when I take the count over here, when I take the count of here is 2, the count of this is 2, the count of this is 1, the count of this is 2, the count of this is 2, 1, 2 and 1, because there is only one item, and therefore the leaves contains the count of all those items which are over there, whereas the interior node will contain the hash tables. This is what I explained over here. See, the leaf node will contain the list of item sets and their counts, whereas the interior nodes contain the hash table. Now, the subset functions what will be there will find all the candidates contained in the transactions. Now here, these are the leaves, and therefore it contains the count, where this H contains the hash function. Okay. Now, based on this one, I get this one. Now, when I am going to particular make the implementation using hash tree, I am going to match like this, and I am getting that I am going to match all those items which were found. Therefore, you might have seen that I found this 15 candidates. These are the 15 candidates. These are the 15 candidates. And from these 15 candidates, you only match a transactions against 11. Now, what I do when I am getting one frequent item, I start matching from the top, and there I am going to check whether the first item belongs to the left hand side or the middle or the right hand side. If I find that it belongs to the middle, I will follow this path. If I find it belongs to the left, I follow this path. And then if it is the right hand side, this will give the right hand side. Now you know what mod function I am using, mod 3, therefore it will map to any one of them. And therefore you search at the top one. Now when you come at the second level, again you will come either in the right hand side or the left hand side or the middle one. If you come in the middle, there are only two numbers. Therefore you can actually check. If you come on the left hand side, you again check whether the second number matches to the left or the right or the middle. If it matches to the left, there is only one number, 145. If it matches to the right, there is only one number, 136. And if it matches to the middle, there are a lot of numbers. Therefore, in that case, you will have to find another hash function. You have to use another hash function, which will map to the either the left or the right or the middle. Now you have to check why this has come here, because at this level 1 matches to the left and even 4 matches to the left. Why this has come in the right? Because 1 matches to the left and 3 matches to the right. Therefore you find that this has come to the left and this has come to the right. Now if you check this one, you check it is 1 that will left, 2 means right, means the middle, and 5 means again middle. Therefore, see, for this one, you check it out. I will just write once more. This is L, then this is middle, and this is middle. And therefore, this L, this one is matched here. This 2 is matched here. And this 5 is matched here. And therefore, I end up in finding the hash tree, the leaf node of the hash tree. Okay. By this method, I will be able to make this particular hash tree. And if I get any transaction, I start matching from here and will follow either the left or the middle or the right. Ultimately, I will match to the second level or third level and will come to the come to the leaf. And when I come to the leaf, I find that I will get that transaction somewhere in the leaf. Okay, this is how you are going to apply the hash tree. I think this is clear to you. Now this is how you are going to improve the support of the support of the candidate keys, because counting of candidate keys, support of the candidate keys is a difficult task, because you will have maybe thousands of frequent items, and in order to maintain those thousands of frequent items, you cannot do a linear search. You have to apply some hashing, some technique which is much faster than a linear search. Okay, you cannot apply a binary search because they are not sorted. Therefore, you have to use a hashing based search technique. Okay. Now this is one example. You can just check it out. This is a simple example that how you are going to, from the database D, you can do this, and it's just a repetition of what we did. Now, there are the methods to improve the Apriori efficiency. Already you know that hash-based item set counting we just discussed right now. Then we can do the transaction reduction. Transaction that does not contain any frequent key item set is useless in subsequent scans. Or we can do partitioning. Now here this is a concept which we will discuss in the very latter part of the syllabus. That what I can do is that instead of maintaining a single data set, I can make a partition of data set. Okay. And now, if I am going to find that any item set is frequent in one of the partitions, it will always be frequent in the original data set. Now, this is called the partition-based frequent pattern mining. Okay. Therefore, if it is frequent in at least one partition, it means it is frequent. Or we can use a sampling approach where we are going to mine on a subset of given data with a lower support threshold, and also to find a method to determine the completeness. Now the meaning is this: if I am going to use a subset of the data set, I cannot use the same support, because if I use the same support, I will not be able to extract the frequent items. For example, there are, say, the data set is given maybe 1 million records with a say support of 1%. If I am going to lower down from 1 million to 10,000, I cannot use a 1% support. I have to also lower down the support level. Therefore, that has to determine what should be a lower support threshold. But just lowering the support threshold will not work, because you should also you have to also test for completeness. Because if you do not test for completeness, what will happen that whatever you are getting out of that may not be complete with respect to the original data set. Therefore, you have to first of all mine with a lower threshold support, and then determine whether the item sets what you generate is complete or not. Okay. Okay, now with this we have discussed the Apriori algorithm, and okay, one more approach which is there, which is not right now given in this slide, but what we can do is that we can do a dynamic item set counting. Now, what is the meaning of dynamic item set counting? That you can add only new candidate item sets only when the subsets are estimated to be frequent. When the subsets are found to be frequent, then only a new candidate item sets has to be put in the data set. And therefore, these are the methods to improve the Apriori. We will discuss it in the very latter part of the syllabus, because you are to the syllabus. You have to cover the Apriori algorithm first.
Excuse me, sir.
Yes.
Certain people are trying to enter the class. They wanted to accept the request. Could you please see?
Just a moment. Okay. Yes, Idris, you want to ask anything? Anybody wants?
I was asking the same question boss had asked, sir. Like to let join other students to join the class, sir.
Okay, tell them to come, because I don't find them here. It's coming and it's going very fast. Why don't I don't know. What I can do is I extend the timing of this so that you will be able to join without having to be asked for. If some issues are there, you just use your microphone, because when I'm presenting, I cannot see your other screen. Therefore, it is difficult if you write something on the in the chat, I may not be able to see that. Therefore, it's better that you use your microphone, unmute yourself, and you can speak. Okay. Now let the people join because one topic remains. I will be just covering it right now. You may join the lab classes at 2:30. I will break of around 30 minutes or more. I'll finish the class in another 15 minutes. You can join the lab from 2 o'clock, 2:30. Okay, now what we discussed is how to improve the Apriori algorithm. Now, partition-based approach of Apriori algorithm is not in your syllabus, but I will discuss those because that might be needed in the lateral part of your work. Okay. Now, even if you are going to apply all these methods like using the hash-based technique to count the support of the candidate keys, or even doing maybe using a partition-based approach, but even these approaches may not be very pertinent if the data set is very large. And normally, data set will contain thousands and thousands of transactions and even much larger number of candidate keys. Therefore, we have to use some other, and moreover, the item sets what we generate from there are not always interesting. If they are not interesting, what happens that even if you generate large number of candidate keys, the end user might not be very interested in getting those many candidate keys. And I also told you that you cannot every time just try to change the value of the support to get all those, because this is a time-taking task. And if you are going to do that, you are going to every time you are going to manage this change the support level, you have to again run the algorithm those many times. Therefore, we apply another concept, what we call is the closed and the max frequent pattern mining, which generates lot less number of item sets from there. And in most cases, the user might be interested to know the max frequent item set or the closed frequent item set than simply a frequent item set. Okay. Now, try to understand it's a simple one, but of course, the algorithm we'll discuss in the next class. Just try to understand this concept well. Okay. Now, let us try to discuss the maximal frequent item set. Now, maximal frequent item set is a subset of frequent item set. That means all item sets which are maximum will always be frequent. Now, what is the frequent item, maximal frequent item set? An item set is maximal frequent if none of its immediate supersets is frequent. Now, try to understand this very well. I want to find those item sets whose none of its immediate superset is frequent. It means that if, say, BC is frequent, no superset of BC should be frequent. Okay? If BC is frequent, no superset of BC is frequent. And if BC is frequent and say BCD is also frequent, BC is not maximal. Okay? Now the meaning is, let's try to understand it. Suppose if I find that BC is frequent, and suppose I find that BCD is also frequent, or say BC is also frequent. If I find that, it means that BC is not maximal. If I find that BCD is frequent, and I also find that BCD is also frequent, It means that BCD is not maximal, and BC is also not maximal because it is subset of BCD. Therefore, this is also not maximal. Therefore, I want to find all those frequent item sets whose immediate superset are not frequent. Are not frequent. Okay, and if I get that, I will be able to find all those item sets which remains over there will remain as a maximal frequent item sets. Okay. Now let us try to just see this slide. Here, if I find that ACE is frequent, if this is frequent, then in that case A will not be frequent. If it is there, then in that case AC will not be frequent. Then A will not be frequent, C will not be frequent, E will not be frequent. Similarly, if I find that BCD is frequent, then in that case BD will not be frequent, D will also be removed, CD will be removed, C will be removed, all this will be removed. And what remains are only three items. Are only three: AD, AC, and BCD. Now, what you can see, the gray boxes, those are the ones which are always infrequent. Why? Because here AB itself is infrequent, and therefore all supersets of AB will be infrequent. Okay, will always be infrequent, and therefore these all will be removed. And similarly, you have to these are always infrequent item sets. Okay. Now let us try to understand this concept. Suppose now let us try to understand how you are going to use a maximal frequent item set. But before that, let me also use a closed frequent item set. Now, a closed frequent item set is an item set if none of its immediate superset has the same support as the item set. Now, try to understand this, the difference between maximal and closed. In maximal, we say that none of its immediate superset is frequent. Whereas in the closed, we say that none of its immediate superset has the same support as the item set. Now in that case, I have to also count the support. In the previous case, I do not need to count the support. Now let us try to understand this. Suppose you are given this data set. Now let us make the counting. Here A contains is 4 times, B 5 times, C 3 times. I maintain that. Then I say D is 4 times, and all I find all those ones. Okay. Now here I find that B over here is having a support of 5. Okay. Then AB is having a support of 4. BC is having a support of 3, and so on. Now let us try to see the other way around. B is closed because no superset of B is having a support of 5. Isn't it true? Because B is having a support of 5 and no superset of B equal to 5. Therefore, B is closed. Got it? Now, AB is having a support of 4. Can you find any other item set which is having a support of 4, which is the immediate superset of AB? No, will not be. Therefore, in that case, AB is also closed. Similarly, if you see BC is having a support of equal to 3, and therefore this is also these are all closed item sets. Now, if you check for this AD, now try to understand this. You check for this AD. AD is having a support of 3. Now the superset of AD is ABD, and ABD is also having the same support. And the definition says that an item set will only be closed if none of its immediate superset has the same support as the item set. It means that AD cannot be closed because there is a superset of AD which is having the same support equal to 3, and therefore this will not survive. Similarly, ABC will not survive because it has a support of 2, therefore this will not survive. ACD will not survive because again you find ABCD is there. BCD could be there, but you have to check that the support of BC will having equal to 3. Now if I apply the algorithm, let me try to show you the algorithm. Okay. Now let us come back to the lattice. And this is the lattice which we discussed. Now, what I can do is that these are database. These are database. These are database D. Now, let us try to find which are the transactions which are supported by A. It is 1, 2, and 4. Therefore, I maintain here 1, 2, 4. Similarly, for B, it is 1, 2, 3. C, 1, 2, 3, 4, so on and so forth. Now, I take some minimum support. Now, suppose if I take a minimum support of equal to 3, in that case, all those transactions which are having less than 3 will go off. If I take a support of 2, in that case, all those which are having a support of 0 or 1 will go. Now, let us take over here, if I am taking the minimum support of equal to 2. Now, if I am going to take a minimum support of 2, obviously here, this will not be there, 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 all this will be removed. All this will be removed. And these are having all equal to 0, therefore this is automatically removed. So this is automatically removed, all those which are having a support of 0, therefore this is all removed. This is not at all equal. Okay? Now you are left with only ones which are having minimum support of 2. Now we come to take this one. Okay? Now let us see about closed. Now let us check the support of C. It is equal to 4. Any transactions which is superset of C is having a support of 4? No. It is not there. Because you find that C is having a support of equal to 4. The superset of C is AC having support 3, BC having support 3, then CD having support 2, ACD having support of 2, and so on. Therefore, C is closed. Similarly, you take the one which you take the one which is there. You take this one. Take this one. D is having a support of 3. Now, any other superset of D having a support of 3? Okay, here D is not there, here D is not there, here D is there, but of course it is a support of only 2. Therefore, in that case, D is also closed. Similarly, take for E having a support of 3. Take the supersets of E, 3, 4, 2, 2, then for E, no more. So this is also closed. And you end up in finding all those item sets which are closed. Now you check here AC. AC is having support of 3. No superset of AC is having a support of 3. Therefore, all these grey ones are the ones which are closed. Now let us try to find the maximal. You remember maximal those item sets whose none of the immediate superset are frequent. Now let us see. Just check for C. C is frequent. But the superset of C, BC is also frequent. Therefore, C cannot be maximal. Similarly, D is having support of 3, but this D is also having a support of is also frequent, and therefore D cannot be maximal. And if you check all this, you will find that only CE, D, ABC, and ACD will survive that test. Just a moment. Okay. Now you find that only these 4 which are blue, which are blue, are the ones which survives the test. Now these ones. And the ones which are which are here, over here as yellow, are the ones which are also closed. And therefore, you find that the number of closed item sets are 9 and the number of maximal item sets are 4. Whereas the frequent item sets are A, B, AB, AD, then CD and all those which are having a minimum support of at least 2 are all frequent. It means that how many of them are frequent? If you count, you will be able to count it out. Now it's so simple, you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Then the 14 item sets which are frequent, 9 which are closed, and 4 which are maximal. All closed are frequent. All maximum are closed. And now we end up into one of the very important observations, that closed is a subset of frequent and maximal is a subset of closed. That means if an item set is maximal, it will be closed as well as frequent. If an item set is closed, it will also be frequent, and therefore this which is holds. That means any item set which is frequent will may or may not be closed and maximal, but the reverse is always true. All maximal item sets are closed and all closed item sets are frequent. And all 3 are frequent item sets. Therefore, we find that the word frequent is written in all of them. and this is the algorithm for, and therefore we are, if we want to find the closed item sets, we will be applying the, the algorithm for closed. If I want to find the maximal, I will apply the algorithm of maximal. But you have to remember that a priori will not find closed and maximal. A priori algorithm is only to find frequent item sets. Is only to find frequent item sets. For closed and maximal, we will be having a different algorithms altogether. Therefore, a priori algorithm only finds frequent item sets. Okay. Okay, now with this, I stop today. And any questions you want to ask, you may please ask the questions.
सर आपने जो हैश ट्री बताया वो जो मॉड 3 करके, सो उसका इम्प्लीमेंटेशन कैसे करेंगे? बस वो क्लियर नहीं हो पाया। मतलब
तुमको पहले हैश ट्री के लिए एक हैश फंक्शन डिसाइड करना होगा। उसके बाद तुम्हें डेटाबेस में लोगे हैश ट्री में हाउ मेनी एंट्रीज यू विल कीप इन द हैश टेबल। ओके, सपोज हाँ,
उसमें सर साइज फिक्स कर दिया 3। रियल वर्ल्ड में साइज थोड़ी फिक्स होगा कि इतने ही सबने 3-3 का ऑर्डर दिया है, कोई 4 का भी ऑर्डर दे सकता, 5 का।
No, the size of the hash table will depend on the number of transactions you are going to encounter. मान लो तुम्हारे पास ट्रांजैक्शंस बहुत सारे हैं, तो तुम हैश ट्री को थोड़ा बढ़ा कर सकते हो, सॉरी हैश टेबल को। अभी होगा क्या कि तुम जब तुम उस पर्टिकुलर नोड को पॉइंट करोगे लीफ नोड पे, तो उसमें मल्टीपल आइटम सेट्स होंगे, वहां तुम लीनियर सर्च ही करोगे। अगर तुम बहुत बड़ा कर दोगे हैश टेबल को, तो लीनियर सर्च बढ़ जाएगा। Therefore, the choice is that how best hash function you design. अब हम करेंगे क्या, पहले हम एक डेटा स्ट्रक्चर लेंगे जो कि हैश टेबल का साइज डिक्लेयर करेगा। फ्रीक्वेंट आइटम सेट मिला, हमने कंपेयर किया उस हैश फंक्शन से, उससे हमारा इस केस में लेफ्ट या राइट या मिडिल पे जाएगा। नॉट नेसेसरी कि 3 ही ब्रांच हो, देयर कुड बी और n नंबर ऑफ ब्रांचेस। मान लो तुमने ऐसा हैश फंक्शन लिया है जो तुम्हें 10 अलग अलग ब्रांच पे मैप करेगा। दैट मींस with one hash table you can have 10 different branches which will map to, but अगर तुम्हारा 10 से ज्यादा अगर तुम्हारे पास एंट्रीज हो गई, तो तुम उस हैश टेबल में अकोमोडेट नहीं कर पाओगे। देन तब तो क्या करना होगा, तो उसको सेकंड लेवल पे जाना पड़ेगा। तुम एक चीज ध्यान देखो, दिए होगे, आई जस्ट रिपीट यू ओवर देयर। Is visible?
Yes,
Okay.
sir.
Now you can see, yeah, at this point, if you see over this point, just a moment. This point, there is only one level. Why? Why I have not made it to a second level? Any idea?
जो सर सेकंड है वो दोनों ही उसी मतलब 3-6 उसी के नेक्स्ट में जाएंगे।
Yeah, because there is only 2 item sets, it can be accommodated in that hash table. But if there would have been say 4 items, then you have to divide. You have to divide this hash table into further down. तो कैसे करोगे? Further down, what you will do is that you will again map with this 3 and 6. और अब तुम सेकंड आइटम पे करोगे 3 या 6 पे। अगर 3 को हैश फंक्शन से करोगे, तो अगर 0 आएगा तो राइट में जाएगा, 1 आएगा तो लेफ्ट में जाएगा, 2 आएगा तो मिडिल में जाएगा। देखो तुम देखोगे यहाँ पे लेवल बढ़ा है, कितनी लेवल पे आया है, 1 लेवल, 2 लेवल, 3 लेवल। यहाँ पे गया है ओनली 1 लेवल एंड 2 लेवल, बट यहाँ पे गया है here 1 level, here 2 level and here 3 level. Therefore, the whole idea is that how good the hash function you find and how much is the size of the table. अगर तुम टेबल बहुत बड़ा ले लोगे, और मान लो उसमें 1000 एंट्री हो गई, 1000 एंट्री, तो क्या होगा, तुमको लीनियर सर्च करना पड़ेगा। मान लो हमें सर्च करना है 458 है कि नहीं, तुम्हारे पास यहाँ पे आया 458, तो तुम्हारे पास आया 458, तुम क्या करोगे, इस हैश फंक्शन से कंपेयर करोगे। पहला आइटम को 4 है तो लेफ्ट पे जाओगे, यहाँ आके तुम अगेन तुम सेकंड वाले से कंपेयर 5 से, 5 जो है वो देगा डिवीजन डिवाइड बाय 2, इसके मतलब ये हुआ कि तुम मिडिल वाले पे आओगे। फिर तुम 8 से करोगे, 8 को फिर लगाओगे मॉड 3 जो आएगा 2, तो इस बीच वाले पे आओगे और यहाँ पे तुम लीनियर सर्च करोगे। 1 to 5 को कंपेयर करो 458 से, नहीं है। 458 को कंपेयर करो 458 से, तो है, तो इसका तुम काउंट +1 कर दोगे। इंक्रीज द काउंट ऑफ 458, क्योंकि हो सकता है ना 458 मल्टीपल बार आए, तो तुम उसके साथ एक सब डेटा स्ट्रक्चर यूज करोगे जो उसका काउंट को रखेगा। Did you get the point?
Yes, sir.
Okay. Therefore, therefore the function which I used over there is too simple. Therefore, that is just an example. But अगर तुम mod 3 लोगे तो तुम्हारे पास क्या होगा, सिर्फ 3 ही तो डायरेक्शन होगा जाने का। Therefore, ऐसा भी नहीं करना है कि ट्री हमारी इतनी बड़ी बन जाए कि हमें नीचे आने में बहुत टेक्स टू मच टाइम, और इतना बड़ा हैश टेबल नहीं लेना है कि लीनियर सर्च बढ़ाना पड़े। Therefore, the hash function what we have to design should be good enough that I should do it in the maybe a good amount, a small amount of time, and I try to find the frequent item in one of the leaves. Any more questions, please? Okay. You stop at this point. Next class will continue from here only. To then upload whatever I taught on your classroom so that you can revise. Try to revise and come, because this will give you an advantage to understand the lectures.